Good morning, everyone. Thank you for joining. We will wait a couple of minutes just in case more people would like to join, and then we'll start. Okay, I think we can start now. Thank you for joining, everyone, and welcome to the second BIOPOLY Cluster webinar, From Waste to Performance, Designing Bio-Based Polymers for Real Applications. Thank you for joining us today. I'm Marta Rodriguez from the Polymer Communication team, and I will moderate this session. Before we begin, I will walk you through today's agenda. First, I will briefly present the BIOPOLY cluster. Then, the project coordinators will introduce their projects, each presenting their approach to developing innovative, sustainable bio-based polymers. Next, we will hear from the technical experts of each project. We will continue with a panel discussion in which our speakers will explore key topics such as technical specifications and constraints, feedstock availability, regulatory frameworks, and the future of bioplastics. Finally, we will conclude with a Q&A session. Please feel free to write your questions in the designated Q&A section at any time. Now, let me briefly introduce the BIOPOLY cluster, which was created in June 2025 and comprises 3 EU-funded projects: Polymer, BIOPYRANIA, and Polymers 5B. While each project focuses on different types of bio-based polymers and feedstocks, from brewer spent grain to agri-food residues and woody biomass, they all share the same vision: advancing sustainable, circular, and high-performance materials that reduce Europe's dependence on fossil-based plastics. Through this collaboration, we exchange best practices and amplify the project's impact. We held our first webinar on November 6, 2025, where we introduced the projects and discussed how to accelerate innovation in bio-based polymers. Now, I'm pleased to introduce our first speaker, Professor Assunta Marocchi, coordinator of the Polymer project. She is an associate professor in the Department of Chemistry, Biology, and Biotechnology at the University of Perugia, where she leads research in organic synthesis. Her work focuses on the valorization of biomass waste for the green production of value-added chemicals and materials, as well as the development of sustainable materials and strategies for energy storage and conversion. The floor is yours, Assunta.
Thank you, Marta. Sorry, I may have done something for which I shared the screen too early. So sorry for that.
No problem.
So just a second. Yeah. Okay. So good morning, everyone. I'm pleased to introduce Polymer, which is a project that started in September 2024 and will run until 2028, which is focusing on the development of bio-based polymer solutions. Polymer aims to create like a sustainable value chain, starting from brewer spent grain, which is the main byproduct of the brewing industry, and transforming it into eco-designed bioplastics for real industrial applications. We focus on three application areas, which is agricultural films, tertiary packaging, and automotive textiles. The project brings together like 14 partners across 8 countries. This includes universities, research centers, small, medium enterprises, and industries. So together we cover like the entire value chain, which is from raw materials to polymer development, processing, scale up, and final application testing. And also sustainability, end of life, and market uptake are fully integrated. Well, the context is rather clear. Currently, bioplastics represents less than 1% of global plastic production, showing like a strong potential for growth. And however, despite this, many existing solutions are still limited. They may be, for example, bio-based, but not recyclable, not biodegradable, or not suitable for real industrial use. And this is where Polymers contributes, and we are developing high-performance bioplastics from brewer spent grain to reduce environmental impact and reliance on fossil resources. And our approach starts from the fractionation of brewer spent grain, recovering lignin, mainly cellulose and hemicellulose. And these are converted into new monomers and polymers through green processes, progressing, as you can see here, from lab to pilot scale to ensure like industrial relevance. And importantly, end of life is considered from the beginning. And biodegradability also and recyclability are integrated into material design and supported by life cycle and techno-economic assessment. Well, Polymer is not only about developing new materials, it directly contributes to key European priorities, including the Circular Economy Action Plan, Zero Pollution Ambition, and Farm to Fork Strategy, amongst the others. At the same time, it ensures compliance with REACH and supporting safe industrial uptake. With this, it's all on my side. Thank you for your attention.
Thank you, Assunta, for your presentation. Next, we had Professor Luis Fonseca, but unfortunately he had a last-minute issue and couldn't join. But you can find his presentation in the recording of the last webinar we held, which is available on our YouTube channel. That said, we will now move to Catherine Vernertz, who is the coordinator of the BIOPYRANIA project. Catherine Vernertz holds a master's degree in chemistry and a PhD in polymer chemistry, focusing on the synthesis and evaluation of stimuli-responsive copolymer architectures through the combination of various polymerization techniques. Since 2012, she holds an academic position at Maastricht University, where she is currently a full professor of sustainable polymer synthesis. Please, Catherine.
Yes, so I will shortly introduce to you the BIOPYRANIA project, where we work on bio-based monomers from second generation biomass for high-performance polymers, copolymers, and blends. So our project started in October 2024 and runs for 4 years. And we have a budget of 5 million euro. The partners come from all over Europe, with a division between SMEs, academics and research centers, and also large industries. We are spread over 9 countries and 13 partners. And the main goal of BIOPYRANIA is to develop a new class of bio-based polyamide and polybenzimidazole polymers and copolymers and blends in a safe and sustainable way from lab to pilot. And these bio-based materials have the potential to revolutionize high-performance applications with a focus on automotive and green hydrogen sectors. So in the green hydrogen sector, we work on membranes, anion exchange membranes for fuel cells and electrolyzers. And we also consider recycling of the materials to enhance the circularity. Furthermore, we have some supporting tools like digital methodologies, environmental, toxicological, techno-economic, and social impact studies. And here you see an overview of our project with the role of the different partners, where we start from second generation woody biomass, that is biofibinol refined, and then the cellulosic sugars and also the lignin will be used by University Saarland and Biobase Europe pilot plant for fermentation. We obtain then amino acids. University Saarland does the academic work, Biobase Europe pilot plant the upscaling. The amino acid building blocks are then converted by B4 plastics to monomers, and these monomers are used to make polyamides and polybenzimidazoles, where Maastricht University does the lab scale work and B4 plastics the upscaling. The polymers are subsequently processed by Arkema into materials that can be used in electrical vehicles by Stellantis, and the polybenzimidazoles are processed by Tecnalia into anion exchange membranes that are used for fuel cells and electrolyzers by Hydrolite. So that's a short intro to our BIOPYRANIA project.
Thank you very much, Catherine. Now we will move on to the technical presentations, and I'm pleased to introduce Professor Fabrizio Saracini, who is representing the Polymer project. He is a full professor and researcher in the Department of Chemical Engineering, Materials and Environment at the Sapienza University, Rome. His research focuses on composite and polymeric materials, with particular attention to sustainability, recycling, and natural fibers. He has contributed to numerous studies on mechanical properties, regeneration processes, and the development of advanced materials for industrial and environmental applications. Please, Fabrizio.
Thank you very much, Marta. Let me share the screen. Can you see the presentation?
Yes.
Okay. So thank you very much for the kind introduction. As mentioned, I'm involved in the Polymer project, and as Assunta already summarized, this project aims to transform brewer spent grains into sustainable and functional materials for polymer applications. And in particular, three different sectors have been identified for our polymer formulations, which are textile, agriculture, and packaging. And in this presentation, due to the limited amount of time, I will only deal with agriculture applications. So let me just frame the problem we are addressing. So, I mean, agricultural mulch films are widely used across the globe, with polyethylene-based films dominating the market. So just consider that around 12.5 million tons of mulch films are used every year. And despite providing clear agronomic benefits, these mulch films also show a significant environmental impact because they tend to degrade very, very slowly, and this actually results in soil accumulation, which produces microplastic formation, and this can absolutely destroy the structure of the soil. It can suppress beneficial microorganisms, and at the same time, it can also interfere with water and nutrient transport. And in addition to these environmental concerns, there is also a strong economic burden, which is associated with their collecting, recycling, and disposing of these material. So this means that there is a strong need for innovation. So the goal is to try to develop high performance agricultural films, which are supposed to be eco-friendly, and at the same time they are supposed to deliver exactly the same agricultural benefits, but as I was mentioning, with a reduced threat to the environment, to the ecosystem. And to achieve these, there are several key strategies that are being explored in the design of biodegradable mulch films. The first one is by blending and structuring polymers, so meaning that we can actually mix together different polymers together with biofillers, for instance, nanocellulose, starch, and in this way we can try to tailor the mechanical performance and also try to reduce the cost of these materials. Another approach is to try to tailor degradation to the crop cycle, and this can be done also by using multifunctional additives. For instance, even blackening agents can, from one side, suppress the growth of wheat, and at the same time increase the temperature of the soil. And of course, a field-driven design approach I would say is essential because, for instance, different colors can serve different purposes. So black films, as I was mentioning, can control the weed. Silver can provide insect repulsion, and so on. And at the same time, all of these needs to be supported by a life cycle assessment to ensure that these materials are really non-toxic and that do not contribute to microplastic pollution and accumulation. So in this framework, the Polymer project aims to explore a very, very promising opportunity. So the valorization of brewer spent grains, which is the major byproduct of the brewing industry. It is produced in very large amounts. It is wet, and I would say it is currently underutilized. So instead of trading it as a waste, what we are trying to do is to actually convert this material, this waste, into building blocks for the synthesis of new polymers. In this presentation, I will show you a slightly different approach in the sense that I will show you how this BSG can also act not only as a starting point from the synthesis of new polymers, but it can also be used as a multifunctional filler itself. And to do that, we are exploring the hydrothermal carbonization of this wet biomass. Hydrothermal carbonization is an example of a thermochemical conversion process, which actually takes place in water at temperatures usually lower than 250 Celsius degrees under autogenous pressure. And in the end, what we get is a solid material, which is called hydrochar, and it can contain a carbon content as high as 60% by weight. This material actually shows quite high specific surface area, and it is very rich in functional groups. So here you can see how the morphology of the wet biomass can be converted to the hydrochar, and in particular we detected a significant increase in the specific surface area. I need also to mention that hydrochar is much more degradable and versatile than biochar, and this is mainly due to the presence of oxygenated functional groups on the surface, and also a lower aromatic structure. And this is particularly important if you want to use this as a filler in polymer blends. So at the very beginning, we decided to check the effects of this filler in a very standard and common bio-based polymer, polylactic acid, and we used a pretty high amount, 20% by weight, and we detected, a few important results. So at first, we detected a significant increase in melt mass flow rate, a decrease in the glass transition temperature and melting temperature of the neat PLA associated with a slightly lower thermal stability. And this was also accompanied by an increase in the residue, and also an increase in the thermal conductivity of the composite. That's why I was mentioning that this can be considered as a multifunctional additive. Basically, one of the major concern was the significant decrease in melt viscosity, melt strength, and this was ascribed to a significant reduction in the molecular weight of this PLA, caused likely by the presence of these oxygenated functional groups, which actually acted as significant transition points during melt compounding. So the next idea was, okay, let's try to reduce this effect, maybe taking advantage of the extensive functional groups which are present in the surface of the hydrochar. Just to mention that, as you look here in the bending properties, the significant reduction in the molecular weight also resulted in a significant reduction in the mechanical properties of the composite. So our next idea was, okay, let's try to take advantage of the surface functionalities, and let's try to modify the surface of hydrochar, and this was done by using phytic acid. Phytic acid is a compound which is very rich in phosphorus, and this is important because actually phosphorus is a natural soil fertilizer. So the idea is, okay, we incorporate this filler inside a polymer, and then in the end, during biodegradation, it can be released in the soil and maybe act as a fertilizer for the soil itself. After the successful modification of hydrochar, we also detected a reduction in the decrease in molecular weight that we experienced before. And as you can see here in the bending properties, we detected also a slight increase in the Young's modulus of PLA, and an enhancement in ductility compared to the unmodified formulation. So this was ascribed to the passivation of some of these functional groups by the phytic acid, and phytic acid was also seen as a compatibilizer with PLA, and this can be seen by looking at the fracture surfaces of the samples. Because, for instance, in the unmodified blend, you can see that it is easy to see the particles of the hydrochar, which are very well exposed on the fracture surface. In the second case, as you can see, it's very difficult to detect the hydrochar because it is completely embedded inside the matrix. So meaning that the interfacial adhesion is somewhat increased. And this is This is our I mean, preliminary results. Of course, the next step was to try to explore different matrices. I mean, less prone to hydrolysis during compounding. Of course, we need also to improve the modification of hydrochar with phytic acid, just to try to increase the amount. And this should be also associated with an optimization of processing parameters. These because we want to reduce or to minimize as much as possible the processing-induced degradation. And here I can show you some preliminary results using another polymer, not PLA. In this case, this is a polymer which is being developed during the polymer project, is a starch-based blend. And in this case, we are also exploring different manufacturing routes. So from batch compounding to twin screw extrusion by changing also the screw speeds. And you can see that basically in this case, the melt mass flow rate is much more constant compared to the previous case with PLA. And it can be tailored by changing the processing parameters. At the same point, we didn't detect a significant effect on glass transition temperature and on melting temperature of this blend. And this was also associated with an increase, this time thermal stability. And if we look at the tensile stress strain curves, you can detect that there is a decrease in the tensile strength, but this time is much more severe compared to the previous case. And this is also supported by, for instance, DMA analysis. As you can see, the glass transition temperature was largely unaffected by the presence of this hydrochar. And if you look at the evolution of storage modulus as a function of temperature, you can see that in this very broad range from -100 up to 50 Celsius degrees, the presence of hydrochar increased the storage modulus. So meaning that there is potential in using this filler, but this should be associated with careful optimization of the processing and also careful selection and design, engineering, I would say, of the biodegradable polymer blend. That's all from my side, and thank you for listening.
Thank you very much, Fabrizio. Now we will move on to Frédéric Bohm's presentation, also from the Polymer project. But first I will introduce him. He's a full professor of sustainable polymer chemistry at the University of Twente in the Netherlands. His research focuses on designing and synthesizing new polymeric materials from sustainable resources, developing degradable and functional polymers, and exploring their applications in biomedicine, agriculture, and material science. Please, Frederick, go ahead.
Thank you. You should be able to see the presentation now. And I would like to show you in the next couple of minutes what my team is up to in the polymer project. So, and especially we are on the beginning of the value chain where we synthesize new polymers and especially focus on their biodegradation and also on their environment-specific biodegradation by producing certain copolymers. And the team has been working already for quite some time on these biodegradable polymers. And I would just like to highlight two papers from the past that we published that I think is interesting for this audience here as well. So one is already quite aged, from 2019, where we asked the question, are biodegradable polymers the plastics of the future? And in this case, we basically focused here on polyesters, normal polyester-like materials. But there's also an update, and so the second part of the movie, where we focus much more on also bio-based and biodegradable polymers, and also a bit more exotic structures, how to control actually biodegradation depending on the environment where the polymer ends up. And there are different, let's say, properties that, of course, influence biodegradation. Let's say simple things are just the size of an object or the chemical structure, but also the environment and different processing parameters, additives, and many things that you do with the polymer before you look at the biodegradation. And what we have seen also in the polymer project, we target different final applications, for example, agricultural mulch films. So of course, soil biodegradation here is important, but maybe for other applications, also water biodegradation in seawater or in fresh water are of interest. And this is what we are at the moment focusing on more conventional polyesters with a few breaking points, what you will see in a few minutes, and also on novel monomers designed from the BSG. And why is this important? So the environmental influence of biodegradation is very strong depending on the chemical structure. So not everything that is labeled biodegradable also biodegrades everywhere. So some polymers only biodegrade at high temperatures, for example, in industrial composting. And I think the most common and also the biodegradable blueprint at the moment is polylactic acid, PLA. And that basically only degrades well in compost. So there's not much happening in seawater. And also in the soil, depending where it ends up as a homopolymer, the biodegradation here is limited. And so you need composites or copolymer structures to incentivize also a biodegradation profile, thinking, for example, of agricultural mulch films. And this goes on and on where polymers might end. And that's maybe a very crowded slide on different polyester materials, basically also polysaccharide materials. And you see in, let's say, red, orange, and green, where they biodegrade and where they're not biodegrade. So sometimes it's not so black and white or red and green here. But many of them have, of course, here a red sign. And that was also what interested us in this project. So how can we also accelerated biodegradation in a certain end-of-life environment, depending on the application. And what we are doing, so we take ring opening polymerization of lactones, and so cyclic ester molecules. And the goal is to use also new monomers that Assunta mentioned from the BSG and make homopolymers. But also what my team is an expert in is using these a bit more exotic cyclic phosphoester monomers, because they can act as viable breaking points. Depending on this microstructure around this phosphorus, you can control here hydrolysis lifetimes selectively. And then we incorporate just a little bit of those into copolymers of these lactones to trigger environment-specific degradation. For example, in the soil, they also release phosphate. That also is, of course, a fertilizer. And there are many of these phospholanes available that we also, some of them we will investigate in this project. And sometimes here you have to look twice where there's a difference in the chemical structure. So they change the hydrolytic stability of the breaking point in the polyester in the end. For example, here in the pink one, there's a phosphor-carbon bond, which will be in the main chain. And phosphor-carbon bonds are hydrolytically stable, but some enzymes, for example, in the ocean can also cleave those. So there are different ways of cleaving them. The synthesis from the chemical point of view is a normal ring opening polymerization. We use normally metal-free catalysts, alcohol as an initiator, and then this would be the homopolymerization. But at the same time, you can also mix lactones in. And that is what our PhD student Sanchi started. And screening different of these phospholane monomers. We see here the postdoc Timo on the team did this already before, looked at hydrolysis half-life times. And sometimes it's difficult to see from the first glance of the monomer structure. Some of them hydrolyze in hours, others are stable for years. And that allows us also to tune here the application. And then inspired by that, so we put it previous to the project already in PLA. So I mentioned PLA is very recalcitrant in seawater, but when you put these breaking points into PLA copolymers, this is now artificial seawater. Here we see a much faster hydrolysis in the red curve. So it's just one example, while the normal PLA also, when the OH group here is switched off, we don't see any biodegradation here. And Sanchi and the team was inspired by Timo's work. So she used then first caprolactone, but also can be, of course, obtained from BSG, but is also commercially available. So it's a good starting point here to see how actually such a 7-membered ring can copolymerize with a 5-membered ring. And we want to do this without any solvent. So we just mix 2 monomers, add a catalyst, and then you get these copolymer structures. And she developed here very nice NMR characteristics. And so where we look here in situ in the polymerization. So you do the polymerization in the spectrometer. And over time, you can follow how the monomers are incorporated and also which neighbor they have. So, for example, is a phosphor-phosphor monomer neighboring, or is there a cross peak between, in this case, a caprolactone and a phosphonate monomer? And she varied a bit the composition. So we see here this is a drift. So all these polymers have a gradient structure, but in all cases, this is here simulation. On the right side, we see that we have these phosphor breaking points along the chain. And so she did this in a statistical polymerization, but she also synthesized block copolymers. So first polymerizing the phosphonate and then adding in the caprolactone, also characterized this. Here's this GPC, so we get a nice molecular weight distribution. And we also know from NMR spectroscopy, this is now diffusion NMR, that the whole molecular weight is shifted in the case of the block copolymers. And what is interesting when you compare now here a block and a gradient copolymer, and this is just a drop cast of the solution. So the right side is a block copolymer, so we get nice crystalline structures. So because polycaprolactone can crystallize, while in the gradient structure, we keep the polymers fully amorphous. And of course, this also influences in the end the biodegradation kinetics where the material end up. And this is what our project partner in Belgium studied in the project. So we have here just two examples, marine degradation and freshwater degradation. And you see the brown curve here, cellulose, as our control sample. And we see in biodegradation, the polyphosphate here is not biodegrading, but it's hydrolyzing very fast. And because of this hydrolysis, when you look here at the red curve in both cases, and so especially here in the freshwater, the red curve is the caprolactone alone. It also biodegrades, but as soon as we have the copolymer structures, the breaking points of the phosphonates accelerate the initial biodegradation rate. This happens in freshwater, but it also happens in marine water. And what we are at the moment investigating is also the phosphocarbon bond actually broken in the marine biodegradation. And it seems to a certain extent this actually is happening. And yeah, what the next plans are, so we also would like to change the mechanical properties. And as caprolactone and also all these lactones are relatively weak in mechanical properties, one trick is to make thermoplastic elastomers. And so we start off with different initiators, 2 functional, 4 functional, or 6 functional groups. Then we polymerize, again, our phosphor monomers or a lactone from BSG, and we chain extend with another one of BSG. And then we get different arms, and the outer segment should be a hard segment, while the inner segment is soft segment. So we get here elastomeric properties, which can be recycled, but also in the end also biodegrade. An additional function that phosphorus brings in is also anti-fouling. So we also can extend even the applications from agriculture to also biomedical applications maybe. One last example, what we want to do, oops, and this animation is a bit off here, is that we also take the BSG and we do a liquefaction process where we just cook the BSG in a bio-based solvent at high temperature and high pressure. Normal liquid products are distilled off, and then we get a solid residue here that actually can be liquefied, and we would also like to include that in vitrameric structures, another strategy to change the mechanical properties. And this black material is interesting from the chemical structure. So it's broken down the lignin structure. When we look in detail in the 2D NMR, I don't go into the details here, but we can compare here different fractions of these liquefied materials. They have similar structure to kraft lignin, but they also have other compounds that you don't see, for example, in kraft lignin. And also there the question will be, how can this be biodegraded or bioassimilated in the soil? Oops. And that was what I wanted to show you, so that we are starting on ring opening polymerization and with a target on environment-specific biodegradation.
Thank you, Frederick. Now from Polymers 5B, I'm pleased to introduce Dr. Michelis Kirplux, who received his PhD in chemical engineering in 2020 from the Faculty of Materials Science and Applied Chemistry at the Riga Technical University in Latvia. He began his research career at the Latvian State Institute of Good Chemistry in 2006, and since 2020 he works as a senior researcher in the polymer department of the institute. Dr. Kirklux has extensive experience in the development and characterization of bio-based polymers. In addition to his academic work, he is the head of the R&D department at Tenex Panel. Please go ahead.
Okay, hello, can you hear me?
Yes.
Okay, so I share my screen and hopefully you see. So today I will be presenting the results that have been obtained in Polymers 5B project and mainly focus on bio-based polymer development for food and wood waste materials. A brief introduction to the Polymers 5B project, as unfortunately Professor Luis Fonseca was not able to come, but I have a few slides regarding the project. So the project is quite broad. We aim to extract monomers out of different waste feedstocks, such as food waste from tomato processing and olive oil extraction, and also wood waste, which is part that I'm mainly working on. And the goal is to extract monomers for polymer development and other components that can be useful and to give a value additional value added to the polymer materials. The project has started in 2024. Total funding is a bit more than 5 million, and the consortia is composed of 13 different partners, from which 6 are research institutes, 1 university for small and medium enterprises, and 2 large companies across the European Union. And so what we do is we want to develop bio-based polymers and plastics for applications in furniture industry and automotive industries, and also textile industries. So regarding the wood waste, in this project we're focusing on the tall oil, which are the lipid part of the wood processing. So when you take the wood biomass and extract the cellulose out of it, you're left with the soapy black liquor. And if you separate it, there is tall oil soap, which is basically fatty and rosin acid soaps. And by acidifying them, you can then further purify it into fatty acid fraction and rosin acid fraction. And for our purposes, we're mainly interested in the fatty acid fraction, which mainly consists of oleic and linoleic acid. And it's quite widely available feedstock on European market, as there are several pulp mills, especially in Northern Europe. What we want to do with this, well, in this project, we aim to develop thermoset materials that mimic polyurethane materials. And polyurethane materials are obtained in chemical reaction between 2 components, 2 liquid components that cure at room temperature, and the curing time is relatively fast. So for this purpose, we were investigating azo-Michael addition reaction between amine functionality and acrylate functionality. And we want to mimic the polyurethane chemistry, that we can change the material properties by changing the functionality of the reacting groups. And we want to have a bio-based component and replace the fossil-based feedstocks as much as possible. As one of these feedstocks, we looked into preamine 1074, which is commercially produced 100% biocarbon content amine, and it is being produced from different fatty acids, such as tall oil fatty acids. And this amine was cured with different type of acrylates with different functionality. And as a bio-based acrylate component, we used soybean oil-based acrylate with an average functionality of 3. And when we combine these bio-based components, then the biocarbon content in the end resin or elastomer is 90.3%. And if we assume that the acrylic acid in the epoxy, in the soybean oil-based epoxide is also bio-based, then we have 100% biocarbon content in the end material. And with other acrylates, there is relatively high biocarbon content in the resin if we compare to typical polyurethane materials. I come from the rigid polyurethane foam industry, and they're economically feasible. It is you can obtain only about 20% bio-based carbon when you use biopolyols in the polyurethane development. And so for this, the main idea was to change the functionality of the reacting components and to see how the properties of the materials will be influenced. And similar to polyurethane chemistry, by increasing the functionality of reacting components, we can change the cross-link density of the polymer network, and thus changing the glass transition temperature of the polymer network and mechanical properties. So here we see that in the DSC experiment that by increasing the cross-linking density of the network, the glass transition temperature also increases. And the same goes for the tensile strength tests. So different cross-link density, increasing the cross-link density of the material will increase your tensile strength. And this is something what is typical for polyurethanes. So if you want to have a glossy rigid material, you use highly functional reacting components. If you want to develop an elastomer, then the functionality of the components is decreased. And why we want to do it? So these are the resins, and what is the purpose of choosing the azo-Michael addition reaction is that we introduce special functional groups into polymer network that after the mechanical degradation of the polymer material, we can grind them and we can reprocess it as if they would be thermoplastic. So azo-Michael thermoset resins have vitrameric properties due to these beta amino polyester groups in their chemical structure. So this is what we did for the azo-Michael thermoset resin based on pre-amine and epoxidized soybean oil, and we reprocessed them. But we got into a problem. So after every reprocessing cycle, our mechanical properties degraded quite significantly. So there is a huge drop in tensile strength properties with every recycling step. And also the glass transition temperature shifted after the recycling of the material. And the drop in the mechanical properties was not so visible if we reduce the repressing temperature, but still with every step we have a decrease in mechanical properties, which is not good. And we try to figure out what is happening there. And we think that we found the culprit. This is the epoxidized soybean oil acrylate component. It has a triglyceride structure with these glycerol ester backbone in middle. And after recycling the material, when the azo exchange occurs, there is a possibility that the released amine can react with this glycerol backbone, releasing the OH group, which afterwards cannot anymore cross-link the network. And the cross-link density of our network is decreasing. And basically, in the end, what happens that we, from elastomer, we obtain just a goo, which cannot be classified as a material anymore. So at the moment, what we're working on, you want to mitigate it. You want to develop a bio-based amine without these glycerol ester bonds. For this, we use tall oil. We produce first the tall oil fatty acid methyl esters. We epoxidize them, and this type of component can be reacted with this bio-based amine and to make one component that has amine functionality. It has biocarbon from the fatty acid components, and it can be it's still liquid, and we can use to make a polymer out of it. And this type of amine was cured with petrochemical based acrylate, and so we saw that the tensile strength do not decrease with each recycling cycle. At the moment, we're still optimizing the synthesis of these bio-based amines. We probably have not achieved full conversion in 7 hours because at 48 hours the material properties are better, and we still need to work on the explanation what happens to young models after the recycling. But the tensile strength stays more or less the same after the recycling cycles and does not drop off. And okay, sorry. And to conclude, so it is possible to mimic polyurethane materials by using beta-aminopolyester resin chemistry to develop vitrimers that can be recycled. And just you need to, well, carefully design the metrics of the polymer that you want to use, because if you add, well, these glycerol-based ester components, then the mechanical properties will not stay the same after the recycling cycles. And at the moment, we are trying to mitigate it by developing allyl fatty acid-based amidoamines to use for the vitrimer development. And well, special thanks to my colleagues, and thank you for your attention.
Thank you very much, Michaelis. And now I would like to introduce our last speaker for today, who is Marilyn Kurst from the BIOPYRANIA project. Marilyn Kurst is the MCC and Sugars Project Manager at Fibinol, focusing on microcrystalline cellulose barrier formulations, as well as the technical aspects of wood-based sugars. She has a background in chemical engineering with hands-on experience in industrial processes and analytical methods, and in her work she is dedicated to developing sustainable solutions that maximize the value of wood-based resources.
Thank you, Marta. Hello from my side. Today I will present how second generation woody biomass can be transformed into high-performance polymers. I will start by introducing the topic and the industrial side of the process, and at the end, Katrin will take over to give more in detail overview of our BIOPYRANIA project. So most materials around us, plastics, coating, fuels, even cosmetics, still come from fossil resources. Fibinol aims to change that. So we are Estonian next generation biorefinery. But unlike traditional biorefineries, which mainly focus on producing biofuels like ethanol, Fibinol goes further. Instead of asking, how can we make energy from biomass, we ask, how can we extract maximum value from it? So the goal is not energy, but materials, chemicals, and sustainable alternatives to fossil-based products. So Fibinol journey started back in 2016 with the sunburst technology. 2018, we entered Sweetwoods project. By 2020, we had our first pilot line. 2023, we commissioned our first flagship plant, and our goal is by 2030 to have our first industrial plant. Our current design capacity is 20,000 tons of C5 and C6 sugars, 7,000 tons of lignova lignin, and specialty cellulose on ton scale, but we are scaling it up right now. But more important than numbers is the concept, industry within planetary boundaries. So this means minimizing waste, reducing emissions, replacing fossil-based chemistry. At Fibinol, we process certified low-quality hardwood and valorize it into lignin, wood sugars, and microcrystalline cellulose. Unlike many other biorefineries, we are able to utilize over 90% of the wood. Now I will explain the process more in detail, we are not just producing one product, we are fractionizing biomass into multiple valuable streams. So we start with hardwood chips. Then the material goes into the pre-treatment line. In this pre-treatment line, we break down wood in about 30 seconds. Like we all know, wood consists of cellulose, hemicellulose, and lignin, and these are normally tightly bound. But in our process, we are able to separate them. And the result is thick slurry. And the slurry splits into the liquid phase, which is C5 sugars, hemicellulose, and solid phase, cellulose and lignin. And after the solid-liquid separation, a C5 sugar stream is obtained, which can be further purified to produce the purified C5 sugars, and also we get from that stream Lignova Light. The remaining solid fraction consists of lignocellulosic mass, which can be directed into two alternative routes. In one route, lignin dissolution and precipitation are applied just to separate the Lignova pure and specialty cellulose. Alternative route is that the lignocellulosic mass goes into the enzymatic hydrolysis, and the enzymes break down the cellulose into glucose. And after solid-liquid separation, we get the Lignova crude and the C6 sugars. The C6 sugars can be also further purified, for example, by absorption. In addition, there is an alternative process configuration where the C5 stream is not separated from the slurry. Instead, the slurry goes directly into the enzymatic hydrolysis, and we get C5C6 sugars. In our process, up to 95% of water is recycled, and heat is also reused between steps. So this is not just a process, it is a highly optimized system. Sugars can be further purified, like I told, and because they still contain impurities such as lignin, HMF, furfural, organic acids. From the image and graph, it can be observed that sugars obtained from our standard process appear as a dark brown syrup and contain dissolved acid-soluble lignin, HMF, and furfural. After the purification step, both the color intensity and impurity levels are significantly reduced, like shown in the graph, where green line is unpurified C6 syrup and the blue line is purified C6. The primary reason for the dark color is the presence of lignin, which contains aromatic structures that strongly contribute to coloration. There are several different purification techniques are available, like, for example, adsorption via activated carbon or polymer resins, membrane filtration, ion exchange, and so on, but it all comes down to purification cost and demand. If we remove acid-soluble lignin, HMF, furfural, organic acids, then we can transform the sugar stream, and it directly affects the fermentation, for example. Microbes are sensitive to organic acids, HMF and lignin, furfural, also catalysis, impurities, poison catalysts, and the final product quality is also improved. So let's take a closer look at the properties of our streams. For the C6 stream, the initial solution that comes out of our system is relatively dilute. After the evaporation step, the total solids increase up to 60 to 65%. The dissolved lignin content is below 30 grams per liter, and while other impurities such as HMF, furfular, organic acids are present at moderate concentrations. Following the adsorption purification step, the lignin content is reduced to below 5 grams per liter, and the level of other impurities are significantly decreased. For the C5 stream, the process begins with the dilute solution. After the evaporation step, a concentrated raw C5 stream is obtained. That means before entering the lignin sedimentation tank. And this raw C5 contains up to 60 grams per liter of dissolved lignin. Following lignin removal in the sedimentation tank, we get standard C5 product, and it has a reduced lignin concentration of below 45 grams per liter. Further purification yields a purified C5 stream with lignin levels below 50 grams per liter. For the combined C5-C6 stream, both dilute and concentrated forms are also available, and this stream contains a significant amount of glycose and xylose. For lignin, we have crude, pure, and light grades, each obtained at different stages of our process. For example, crude lignin is derived from the C6 process and has a slightly lower lignin content. In contrast, pure lignin is obtained from the MCC production process, where the lignin content is higher and the carbohydrate content is lower. So, where to use our produced materials? Our applications include insulation, coatings, packaging, constructions, personal care, chemicals, and so on. So through projects like BIOPYRANIA, we are not only replacing fossil materials, we are redesigning entire material systems from the ground up. The key idea of the project is to produce the pyrazine-based monomers from second generation biomass. So our role in this project is very important. We provide the starting point of the whole value chain, the biomass-derived raw materials. And this shows that Fibernol is not just producing materials, we are enabling entire new value chains. So Katrin, you're next.
Yes, so now I will tell what we have achieved up to now, starting from the Fibernol biomass. So the people from Saarland University, they have done strain and bioprocess development in order to obtain amino acids. And one amino acid was obtained from the Fibernol C6 syrup. And we targeted a titer of 50 grams per liter, and we reached 91 grams per liter. And we also compared it using pure glucose instead of the syrup, what gave similar titer. A second amino acid had a targeted titer of 10 to 20 grams per liter. We are still at shake flask level, where we are not yet at the targeted titer. We have now 1 gram per liter. And if you go to the next step, before plastics used amino acids to make monomers. And we have two monomers. One monomer was already prepared at 500 gram scale. They seriously improved the starting lab scale protocol to the current one with respect to safety, energy use, and yield, with a 10% yield increase. And for monomer 2, we are at 100 grams scale, and the yield still has to be improved. And those monomers were used by Maastricht University to make polyamides and polybenzimidazoles. So if we go to the next slide. For the polyamides, we developed a route to make polyamide homopolymers, and depending on the choice of the diamine, we can achieve melting points between 120 and 280 gram centigrade, and molecular weights 20,000 to 110,000. Physical properties of polymers and copolymers are currently under investigation, where Arkema is blending those polymers with, for example, reinforcing agents. And we are currently in the stage of scaling up the polymer to 100 gram scale. For the polybenzimidazoles, synthesis of polybenzimidazole in a green way is still very challenging. But we made some polybenzimidazoles from our monomer, and we also post-modified them because you have to introduce charged groups to make those polymers anion conducting, because we want to use them as anion exchange membranes in electrolyzers and fuel cells. And samples were transferred to Tecnalia for testing and processing into membranes. And the next slide, I would like to acknowledge all the members of our consortium. I would like to thank you for the attention.
Thank you very much, Marlene and Katrien. Now we will move on to the panel discussion, where we will welcome all the speakers. We will explore the opportunities and challenges for bio-based polymers in a circular future. And to do so, let's start with a basic but very relevant question. Can bio-based polymers match high-performance specifications? Fabrizio, Frederick, would you like to say something?
Maybe I can start. Of course, high performance is always a question of what do you want to perform? And I think for bio-based, it's possible. And so we have seen rigid materials that can reach, for example, high glass transition temperature, and also recyclability. For biodegradable, this might be a bit more challenging because, of course, breaking down these very rigid bonds is not so easy. But I think they're also thinking, for example, fungal degradation. This also might work.
Okay. As Frederick was mentioning, yes, it depends on the sector that you want to explore. Because in some cases, for instance, rigid packaging, I mean, conventional bio-based polymers are already comparable with traditional fossil-based plastics. The problem is when we want to, I would say, explore different sectors, much more challenging, like, for instance, I don't know, the automotive or even aerospace or high temperature electronics, because actually currently these bio-based polymers suffer from lower thermal stability, an excess of moisture sensitivity, and especially in some cases processing challenges. And this actually is still limiting their industrial use. So I would say that the answer to your question is yes, bio-based polymers can match high performance specifications, but only in certain domains, because what we are still missing, according to my point of view, is an extreme resistance to high temperatures, durability, and for instance, long-term stability. These are still issues under consideration, I think. But the field is evolving quite rapidly, and so I suppose that with continued material innovation, bio-based polymers can likely meet a broader range of applications. But these are, according to my point of view, still the limitations right now.
Great, thank you for your answers. Would anyone like to add something? If not, let's move on to the second question, which is, how do you deal with feedstock variability? And I invite Assunta and Merlin to answer to this question, as well as anyone else who wants to participate.
Yes, thank you, Marta. Let's say that variability is actually a key issue for us because in polymer, as already said, we are working with brewer spent grain, which is inherently variable. And this depends on the raw materials, depends on the brewing process, and so on. So our approach is like to manage this variability rather than trying to eliminate it somehow. So what does it mean? This means, first of all, properly characterizing the feedstock, fractionating it into its main components like cellulose, semicellulose, and lignin, so that we can work with more controlled systems. And on the process side, developing formulation, for example, and processing strategies that are robust enough to tolerate this variability. So what I really think is that the idea behind should be really to design the system to be flexible, because variability is like part of working with bio-based resources. So it is not really a problem to fix, but rather a condition to work with somehow.
Yeah, and from Fibanol side, we deal with feedstock variability with applying highly controlled process that removes the variability at the early stage. We have up to 50 different quality set points. The most sensitive parameter is the C5 composition for us. This is actively controlled in a pre-treatment line. In addition, for example, C6 conversion is managed through controlled enzyme dosing. In terms of raw materials, we can use both roundwood and plywood residues, but we like the plywood residues more because they are always dry and they originate from the most consistent part of the wood. In Estonia alone, there is approximately 80,000 to 100,000 tons of plywood residues available annually, so this is not an issue. And also we rely on empirical control with approximately 30-minute residence time.
Great, Bear. Thank you very much for your answers. And let's move on to the next question. Bringing these innovative materials from the lab to the market is often a huge challenge. What are the biggest technical bottlenecks? Michaelis, Merlin?
Yeah, so the biggest technical bottlenecks, of course, is the upscale and the TRL level, which we all know, and these are the problems. So, and that's why, well, European Union is giving the investment in the projects with a higher TRL. I'm guessing the Fibanol is more experienced with that because they are, well, based on a European flagship project, which is a very good incentive if you want to ever commercialize these technologies, because, well, bio-based technologies, they need to catch up to petrochemical industry, which has been active for the past 100 years, and they have optimized everything possible. And only by increasing the TRL and reaching the industrial optimization, the bio-based technologies can hope to catch up to the petrochemical industry.
Yeah,
so
agreed. And also from the Fibanol side, the complexity of the wood is one of the bottlenecks because there is never a perfect or ideal separation. So this means chemical reactions can continue and may affect equipment. For example, C5 stream can precipitate in pipelines. So we have to make sure that the equipment is really fit for us. We know that chemical industry equipment is highly optimized, but we are using it for more complex bio-based materials. So this requires additional monitoring and adjustments.
Perfect, thank you. And let's move on to the regulatory framework. What regulatory frameworks, standards, and incentives are needed to support the adoption of bio-based polymers while ensuring that they meet safety, performance, and end-of-life requirements? Fabrizio, Catherine?
I start? Okay. Okay. So I can start and then I leave the floor. For sure, one problem, according to my point of view, is in some cases to be very specific on the definition of these materials, because sometimes, as Friedrich was mentioning in his presentation, there's a confusion among the different terms. So in many cases, bio-based, biodegradable, and compostable, they are considered exactly the same, and this is of course not true, because actually these misleading claims can also lead, I would say, to greenwashing and also improper disposal of these materials. So we need, I think, some kind of application-specific rules that ensure that these materials are used only where they provide a real environmental benefits. And another point maybe is to try to harmonize together all the different regulations, because sometimes, I mean, there are some key standards for compostability, the bio-based content, for the soil biodegradability. But in many cases, we need to, there are some misalignment between, for instance, ISO or ASTM or other, regulation at the regional level. And there are very, very few standards dealing with, for instance, long-term stability of these polymers. And this is something that should be, I think, solved. And also to try to consider all the degradation conditions, for instance, also including marine biodegradation standards. This is something that needs to be addressed. And another point, I would say that from the policymaker point of view, maybe we should try to include the life cycle assessment as a real decision-making tool, because in many cases it is not enough that some material comes from a renewable origin, but we should actually include all the life cycle of this material to say, okay, this is convenient for the environment or not. So this is something that should be included in a much more, I would say, solid way in the framework of rules and regulations. I think these are the most important points that that need to be addressed.
Yeah, and what I want to add to that is with respect to safety, for example, we have frameworks like REACH in place, but it's not enough to just look at the polymer or the monomer, but we also have to look, for example, at degradation intermediates if we are looking at biodegradable polymers, or at impurities in the biomass or in the upon biorefinery. And for the rest, I think Fabrizio has covered everything.
Thank you both for your answers.
Maybe,
And now,
maybe Martin, if I can add just, following this statement, maybe another point that might be considered is that we need also investment in economic investment. I mean, in industrial composting and recycling infrastructures. This, I think, would increase the adoption of this material.
yes, thank you for this addition, very relevant. And now I would like to move on to the future and what needs to happen in the next 5 years. And for this question, I invite all of the speakers to answer as a way to conclude the webinar. Yeah, go right ahead, Michaelis.
Okay, I will have maybe unpopular opinion. So I would say the next 5 years, as a European community, we should stop subsidizing petrochemical industry and start higher taxation on the, well, pretty much carbon emissions out of all the processes. Because at the moment, we're not considering economically what will be the influence of the carbon emissions in the future.
I think this is a good point. So I fully agree to that. And so we should focus really on bio-based materials. And also as academics, I think we should also keep our minds open for some exciting new structures and to explore the possibility of this new playground besides, let's say, conventional polymers, commodity plastics that we can achieve with the bio-based materials.
Yes, and I think we should also keep in mind that we design the polymers also not only bio-based, but also for end of life. So not just think, can we make something that's equivalent to what exists now, but can we solve the whole, or can we, with one polymer, have several targets, bio-based and recyclable?
Yeah, and maybe also to add to that, so not only the magic drop-in solution that big industry always wants will be the solution. So we have to keep our brains open for also changing running things and steps. So in industry.
I would add that in the next 5 years, maybe we must deliver also a strong diversification into non-food feedstocks. I mean, we need to be able to have, I would say, as Frederick was mentioning, I mean, more biomasses to work with, and also that I mean, these biomasses are available at scale, industrial scale, of course, to work with and to deliver new solutions, which are actually new materials and not just a sustainable alternative to something that is already in play.
Yeah, totally agree. We need to continue the shifting the mindset, but there also has to be the collaboration across the whole value chain. No single player can solve this alone. So biomass processors, chemical companies, material producers, and end users must work together.
Yeah, and also I think at the same time, the success of these bio-based materials in general will also depend, let's say, on whether industries are willing to redesign products and processes around these material themselves. So not just replacing one with another, but really redesign it also in consideration of what we mentioned before about the variability, intrinsic variability of the biomass feedstock.
Thank you very much for this insightful discussion. And now let's move on to the Q&A. I see that there is a question from Amine Buseta asking if lignin can be used as a high-performance coating, given that it is non-film forming. Are there any industrial applications?
Okay,
Well,
I will take.
Oh, yeah.
I will take that one. Not alone, lignin has to be mixed with other materials or like chemically modified. There are like lignin-based polyurethanes available right now. They really improve the lignin improves the UV resistance, for example, and makes the product more like bio-based.
Another one from Amber Wind. What is the biggest bottleneck of using brewer spent grain as a filler today?
I can take this one. I mean, if the question is about using BSG as it is as a filler in a polymer, The main problem right now is, I think, the fact that this bio-based filler is wet. It contains around 80-85% of moisture. So the problem is that if you want to use it, you should add for sure a pre-drying step. That can be quite energy intensive at the moment. So that's why, for instance, we decided to use and to switch to hydrothermal carbonization, because this process can work directly on wet biomasses, on the contrary of for instance, producing biochar by pyrolysis. And this is actually a great advantage, because actually you should dry it, and it takes a lot of energy, a lot of time, and it can be quite energy and intensive and expensive. I don't know if Assunta wants to add something else, but I think that at the moment, as far as I am concerned, this is one of the biggest issues.
Yes, definitely.
Okay, thank you. And then we have a follow-up on the lignin question, which is, can lignin nanoparticles be used as a film coating, as a standalone coating?
Maybe I can say something to that. So the brief answer is yes. So we tried this in the past in the research team, but we were not successful in getting, let's say, good properties of this coating. So it's a relatively weak coating. Maybe with additional cross-linking or sintering, this might be achieved. I would say potentially yes.
Perfect. So if there are no more questions, I will move on to the conclusion. Oh, okay, we have another one. Is the price of the final biocomposite with BSG as filler competitive?
Is the price?
Is the price of the final biocomposite with BSG as a filler competitive?
Right now, we didn't perform some technical economic assessment, because actually we are in the really early stages of testing this hydrochar as a filler. So I don't have an answer right now. But the process itself to convert the wet BSG to hydrochar, I mean, it's carried out in water. At temperatures which are not very high. I mean, as I mentioned, lower than 200 Celsius degrees, so it is not very energy intensive. But I cannot be more precise than this at the moment.
Okay, thank you for your answer. And with this, we have reached the end of our session. Thank you once again to all our speakers for their insightful contributions, and to everyone who joined us today. Today's webinar continues as collaboration as the BIOPOLY Cluster, which is based on shared goals and ideas. And we look forward to continuing this journey together and to welcoming new partners in the future. So stay tuned for that. The webinar recording will be available on YouTube in the next few days, and will also be shared on the project's social media accounts. So be sure to follow us there. Thank you once again for joining us, and have a great day.
Thank you very much.
Thank you. Goodbye.
Thank you. Bye.
Thank you. Bye-bye.